Today is section 8.3. We're learning about combinations. In our last lesson, we learned about permutations. Permutations is an arrangement of possibilities or outcomes where order matters. Meaning, if I have 3 spots, being put in order ABC is not the same as BCA, and it is not the same as ACB. Okay, so in permutations, the order matters. This is first place. This is our gold medal. And the gold medal is the best. Gold medal is first. And this order definitely matters with a permutation. On the other hand, in combinations, order doesn't matter. So I can have, let's say I have some M&Ms, and I pick 2 at a time randomly, and I get a green and a blue. Well, picking a green and a blue, they go in my mouth, they mix up, they still taste the same, and it's going to be the same thing as grabbing a blue and a green. It doesn't matter. This is one group. So the order doesn't matter in a combination. Order does not matter. Okay, in any given set of objects, there are more permutations than combinations. So if I have a set of numbers, I think yesterday we looked at 101 and 3. The permutation of 101 and 3 was 101 times 100 times 99, which was 999,900. Okay, our combination is going to be lower than this. The permutation will always be bigger than the combination. There are always more permutations than combinations. Okay, so what we're going to look at is how many different ways can 3 representatives be chosen from a group of 6 people. Okay, so first we have to find the permutation of 6 people taken 3 at a time. So we have the slots 1, 2, 3. We multiply 6 times 5 times 4, and that gives us 120. And since order is not important, we have to divide the number of permutations by the number of ways that 3 things can be arranged. So we take 120 and we divide it by 3 times 2 times 1, which is the same as 120 divided by 6, which is equal to 20. There are 20 ways that the representatives can be chosen. So this symbol, C, for combination of 6, 3, represents the number of combinations of 6 things taken 3 at a time. And just what we did before, we have 6 times 5 times 4 over 3 times 2 times 1. So here's an example. Let's find the combination of 8, 5. The combination of 8 and 5, we start out by doing the permutation of 8 and 5. So we have 5 slots, 1, 2, 3, 4, 5, 8, 7, 6, 5, 4. And then we take that number and we divide it by the number of possible arrangements, which is 5 times 4 times 3 times 2 times 1. So now we want to look and see, well, can we do some cross cancellation? We can cancel out the 5s. We can cancel out the 4s. We can cancel out 3 and 2 to get 6. Now we're left with a much simpler problem to solve. 8 times 7 is 56. 56 over 1 is 56. So there are 56 possible combinations when there's 8 objects arranged in 5 slots where order doesn't matter. Okay, let's do one more example. Let's look at the combination of 7 and 2. So we start out with the permutation. There's only 2 slots, so that's 7 times 6. And there's since 2's there, the bottom is 2 times 1. We can do a little bit of cross canceling here. I can cancel the 2 and make the 6 into a 3. 7 times 3 is 21, all divided by 1. So my possible outcomes is 21. Now you try. Find the combination of 8 and 3. And the combination of 16 and 3. Once you have your answer, you can unpause it and see if you got it right. Okay, as you can see, I'm using the cross cancellation to make the mathematics easier. So for the first one, I have 8 times 7 times 6 over 3 times 2 times 1. The 3 and the 2 can cancel out the 6, and all I have to do is multiply 8 times 7 is 56. Okay, the second one, 16 to 3, so I have 16 times 15 times 14 over 3 times 2 times 1. My 3 and my 15 cancels my 3, and 15 times 5 is 3, so then I keep my 5 there. The 2 and the 14 can cancel out and change the 14 to a 7. So now all I have to do is multiply 16 times 5 times 7, which gives us 560. And this is how you can find the total number of outcomes of a combination, which is an arrangement or listing where order is not important.